All right. For those of you who don't know me, my name is Chris Glover, and I work in the Energy Recovery Restoration Department here at Airxchange, which is just a kind of a fancy way of saying I work with folks that have these devices in existing buildings. And today we're going to talk about some of the practical guidance that's being offered by most nationally recognized standards these days for ventilation in educational spaces. Just a little disclaimer saying that we try to create a narrative that appeases to almost everyone that should be in here. So hopefully you learn a little bit as you join in today. So just a quick background on Airxchange. We were founded 40 years ago in Rockland, Massachusetts. For those of you who don't know where Rockland is, it's about 20 minutes south of Boston. We have over 300,000 components in the market, and that is growing year by year. We are a charter member of the AHRI ERV committee. We are a member of the ASHRAE 90.1 Mechanical Subcommittee. We are a member of the 62.1 Ventilation Committee, and we are also a member of the TC55 Energy Recovery Committee. We're currently the largest in volume supplier to HVAC OEMs in the United States, and all our products are AHRI 1060 certified for performance. Okay, so prior to beginning the discussion, I just want to point out that the focus of this presentation is going to be on general ventilation and energy recovery guidance, and not necessarily specifics to the system design. The current state of the HVAC systems in schools varies quite a bit across the country, so every location and their facility is going to be somewhat unique in their own regard. Also, as we begin, it's worth noting that schools and universities are the largest vertical market for energy recovery technology. And right now, there's a lot of discussion on the operation of the ventilation system, but with little being said on energy recovery. So I think it's very important that we tie the two technologies together. So on the agenda today, where I'm going to go briefly over the overview ventilation and dilution. We're going to view the operational guidance coming from ASHRAE and CDC. We're going to review the energy recovery technology operation. I'll go over the inspection and evaluation of existing energy recovery systems. I'll then go over cleaning and remediation of existing energy recovery systems. And then at the end, I'll end with the sources and some resources that are available to you. Okay, so let's take a look at a typical ventilation process. The outside air comes into the HVAC unit. That air is then conditioned to a point where it's acceptable to be delivered into the space. That fresh air then dilutes the stale space air, which is displaced and exhausted outside the building. So the benefit of ventilation is dilution. Dilution in its very basic form is the continual reduction of concentrations of contaminants of concern. The rate of airflow delivery into the occupied zone is typically presented in cubic feet per minute, or sometimes referred to as air changes per hour, which is essentially the rate of airflow delivery as compared to the volume of the entire space. It refers to how many times per hour the entire volume of air within the space is completely replaced with fresh outside air. So once again, the dilution is the continual reduction of a contaminant source with the introduction of fresh outside air. The generalized dilution curve that you see on your left is often is often used to represent the reduction of contaminants based on a normalized airstream. And what it represents is that every time you double the air changes, you cut the indoor concentrations of contaminants in half. So this generalized curve is typically used to represent what most consider kind of normal occupied space air, and it doesn't really stem from any type of viral or health-related concern. But that's not saying there isn't a long history of studies that demonstrate that this curve has been used to form a relationship with risk reductions as you increase outside air. So the science behind reduced infection rates as it relates to ventilation is most often attributed to what's known as the Wells-Riley equation. Back in 1955, Wells developed a way to calculate what's known as a quanta of infection. A quanta of infection is a unitless hypothetical infection dose rate. It wasn't until 1978 that Riley came along and took the quanta and developed a risk assessment model that established an infection rate reduction with increasing rates of ventilation and quanta. And looking at that relationship, it can be demonstrated that the process follows a kind of a similar curve to that of the general dilution curve. The Wells-Riley equation has gone through several updates over the years to include additional technologies like filtration and UV light, and has become what's known as the modified Wells-Riley equation. And the real reason I'm going into such details, I want to demonstrate that ventilation, filtration, UV are all additive, and they hold equal weights when you're determining the strategies for risk reductions in occupied spaces. So what determines the ventilation rate in commercial buildings? ASHRAE Standard 62 is the ventilation standard for acceptable indoor air quality in buildings. I'd like to state that the standard itself is not a health standard. Disease transmission was not considered when developing these rates. It strives to provide guidance that provides health, comfort, and occupant acceptability, but doesn't guarantee it. More recently, ASHRAE and the Board of Directors approved a rule stating that ASHRAE standards shall consider health impacts where appropriate. But all in all, those rates are largely based on what it takes to dilute a normal source of contaminants. Now, what is a normal source of contaminants? Well, it's typically bioeffluent, which is coming from contaminants coming from the building occupants, which are most often odors, and off-gassing from building materials and furnishings, or any processes that may be occurring inside that space. And with all those elements taken into consideration, provides the minimum ventilation rates to achieve dilution. Now, I highlighted minimum here because I want to stress that as most code-related mandates go, the minimum often becomes the maximum. And recently, with the pandemic going on, it's been kind of demonstrated that the rates attributed to reducing health risks are often attributed to the higher ventilation rates above what the minimum rates are. So looking specifically at the sample rates for educational spaces, there are 3 paths for compliance within the standard. So you have the ventilation rate procedure, you have the indoor air quality procedure, and you have the natural ventilation procedure. The one that's most commonly used is the ventilation rate procedure, which is a function of the number of occupants and the square footage. What's fairly unique to educational spaces is they represent some of the higher occupant density spaces, meaning these spaces traditionally have higher ventilation rates associated with them. Sorry. So if ventilation is so important, and why aren't we as a community just dumping tons and tons of outside air into the space? And well, it's because it takes a lot of energy to condition that air. So looking at the psychrometric chart on the left, what you're seeing in that dotted line is what on any given day at any point in the country, what your outside air conditions could be. That's a pretty big operational window. The red dot and the blue dot represent your typical indoor air conditions in both heating and cooling modes. So as you move away from those points, the bigger the energy load is going to be on the building. So essentially, the hotter it gets, the colder it gets, the more humid it gets, the more energy you're going to use to try to condition that air to a point that's acceptable for the space. Also, because you have this big operational window, it means that designing a system that can operate efficiently with all these conditions in place can be, quite difficult. So energy recovery has really been developed to respond to those challenges. The easiest way I can describe what an energy recovery process is that all this device wants to do all year long is bring the outside air condition as close as it possibly can to the indoor condition. And depending upon how effective that device is going to determine how close it actually gets. It does this passively, meaning as long as there is a difference in thermal energy or moisture, this device is going to be working to perform that process. Typical energy recovery systems reduce the energy load by the ventilation system, typically between 50 and 80%. You can get higher efficiencies if you design for it, but most common systems are going to kind of reside in that window. So once again, looking at the psych chart at the left, and I'm not trying to make everyone here a psychometric expert, but I think it does a pretty good job of giving you an image of what the system does. What it does is it takes what is that dotted line, that large operational window, and shrinks it down to that solid line. And really the difference between the two is your energy savings. So that that reduced operational window provides greater energy savings, and also provides more ideal conditions and more predictable control for maintaining occupant comfort in the space. The next section, I'm going to go over some sources where you can find some operational guidance as it relates to educational spaces. I'd like to preface this statement by saying that there's a lot of fragmented sources out there of information right now, and new information is continually coming in, although it has kind of somewhat settled in the past couple of weeks. I'm an HVAC engineer, so I've largely been following what's been being discussed by ASHRAE and the CDC and other building related communities. So the guidance that I'm going to present is really kind of like the high level messaging, not necessarily the specifics on how you're going to accomplish that, but what you should be trying to accomplish. Starting with ASHRAE, the documents that I believe that are most important for this particular topic are the ASHRAE position document on infectious aerosols. This was kind of the first technical piece that was written by ASHRAE, and it was developed by the ASHRAE Epidemic Task Force. And the purpose really set the tone and the direction the task force was going to take during the epidemic. Also, you have the core recommendations for reducing airborne infectious aerosols. So it's a one-page document that kind of summarizes all the core recommendations. The one-page guidance for reopening schools, the ASHRAE reopening schools and university guidance, and lastly, the practical guidance for epidemic operation of energy recovery ventilation systems. So the ASHRAE guidance is largely based on the mechanical operation guidance, and that has been translated kind of over to the CDC with a similar tone, or even the same guidance being presented by both sources. So, however, the CDC includes additional guidance as it pertains to kind of source control, sanitizing, traffic flow patterns, and more in that regard. But the focus on this conversation is going to be the mechanical operation. All right, so the big takeaway when reviewing these documents, and there's a couple hundred pages worth of documents here, is the importance of ventilation as a means of mitigation. So, ventilation with effective airflow patterns is a primary infectious disease control strategy through proper dilution, which basically states you're going to want to keep your ventilation system operating and optimize it to the best of your ability to provide proper dilution. You're going to want to provide at least the required minimum outdoor ventilation rates as specified in Standard 62. Now, for some folks listening in, that may be difficult. Existing units operate over time and have a tendency to get less efficient. So this applies to the airflow delivery as well. If you have the ability to flush the space between occupied periods, the current suggestion rate is to provide a flush equivalent to 3 air changes. Once again, this may be easier said than done for certain spaces. Limit reentry of contaminated air that may reenter the building from either recirculation or reentrainment. So keep this in mind because I'm going to discuss this in detail in a couple of further slides. Use a combination of filters or air cleaners to achieve MERV 13 or better levels of performance for air. Now, I highlighted recirculated here because understanding of how recirculated air is required for this, achieving this step, and I'm going to talk about that again in a couple of slides. Okay, so disable any demand-controlled ventilation. So carbon dioxide is often used as a reference gas to determine occupancy, and its purpose is to minimize outside air based upon occupancy. Since most educational spaces are being used or will be used at part occupancy at this point, you don't want the control algorithm to inadvertently lower the ventilation rate. Increase the ventilation rates above the minimum rates to the maximum allowable per the device without compromising thermal comfort or humidity control. And if the building is considering replacing or designing a new ventilation unit, size that unit for 150% of the code mandated minimum flow for periods of crisis. I would like to say that, and kind of as a word of caution, when taking all these items into consideration, when changing the operating parameters of an HVAC system, there may be both intended and unintended consequences that will happen. So you want to make sure that you have a good understanding of the system effect before making or implementing any of these changes. Aside from the general guidance that I mentioned, there are prescriptive guides available specific to educational spaces. Prescriptive guides offer really kind of like a blueprint or a checklist that you can follow for space preparation. The three that I'm going to mention here are the ASHRAE, or excuse me, it says the K through 12 COVID-19 mitigation toolkit on the CDC, the ASHRAE reopening guide for schools and universities, and the Harvard Healthy Buildings risk reduction strategies. That's a tongue twister for reopening schools. All of them provide basic mechanical guidance, but really only the ASHRAE document has a section specific to energy recovery devices. So if your facility has an ERV, you're going to want to reference that document. Within that document, there is a reference to a document that I'm going to talk about shortly, which is the TC55 practical guidance document. Okay, so as we discussed the operational guidance for the ventilation system, what if your system is equipped with an energy recovery device? So here's some guidance as it relates to energy recovery. Well, first and foremost, a well-designed and well-maintained air-to-air energy recovery system should remain in operation. Now, you may be asking yourself, what does well-designed and well-maintained mean? Well-designed refers to proper fan location and operating pressure, and that the ERV component has been sized with proper velocity and pressure drop in mind. And the seals have been designed and selected for and adjusted for that application. Well-maintained means that the system was installed, tested, and balanced appropriately, and that the building operators have been following the manufacturer's instructions or recommended instructions for any particular maintenance procedures. And in order to minimize potential concern for carryover, I'm going to talk about that in the next couple of slides. So next couple of slides are going to quickly review the basics of how energy recovery works. Some of this is probably a refresher, but I just like to include it in here because we have a pretty wide audience here. So some of you may remember this slide from earlier in our conversation. I'm taking that same system, but adding an energy recovery component into it. So you're performing the same process, but I often refer to energy recovery as a load shift. So you're essentially shifting the conditioning load of the ventilation air from the primary heating element over to the energy recovery device that is conditioning that air using the low-grade thermal energy that's normally exhausted outside the building. By using the low-grade energy instead of a high-grade energy like a gas or electricity, it greatly reduces the amount of energy consumed to treat the same amount of ventilation air. So you can see, oh, didn't mean to do that. So you can see that the air still comes into the unit, but instead of the heating and cooling coil treating the air, you're now shifting it over to the energy recovery component. The energy recovery is going to recover and precondition the air and deliver it into the space for dilution purposes. All right, now I wanted this slide. So it's important to recognize the difference between the sources of recirculated air inside the space. If the HVAC system is, just pumped outside air in and exhausted it immediately, it would be exceedingly costly to condition that air. So what a typical HVAC system does is it recirculates a portion of that air to temper it, so you can maintain occupant comfort. So the system recirculation accounts for what in most systems, 95 to 99% of all the recirculated air within the space. Now, recirculated air can either be co-located or separate from the exhaust air stream. So let me just put that. So in that, what I just drawn there, systems like rooftops and air handlers like System A often have co-located exhaust and return air streams and provide a mixed air stream consisting of both outside air and filtered recirculated air. Or you can have systems like System B. And system like B would be examples that would be fan coil units, VRF, PTACs, where one system is handling the outside air and one system is handling the recirculated air for occupant comfort. You also have to be aware of any reentrainment. So reentrainment is when exhausted air inadvertently enters back into the space air through the outside air intake. Now, there is a small amount of recirculation that happens at the energy recovery component. But when you take that percentage into account the entire system flow and the system recirculated air, it's usually magnitudes below what reentrainment or recirculated air is in terms of returning space air back into space air. So if the energy recovery component is AHRI certified, the recirculation of air is a certified value. So in this particular context, it's called EATR, exhaust air transfer ratio. EATR is a value represented as a percentage, and it's a percentage of the outside airflow, and it gets taken into consideration when designing the fan system. So you're going to have to maintain the net flow to make sure that you're delivering an adequate delivery of ventilation air to the space. Per the ventilation standard, you're allowed to recirculate a certain percentage of air depending upon the class of air you're exhausting. Those levels are 5 and 10% depending upon the class of air. However, most modern designs have recirculation rates that are usually well below that, somewhere in the 1 to 3% area. And it's really important to keep in mind that EATR is a function of outside air, which is usually the lower of the two airstreams when you can compare outside air to recirculated air and calculating your total system delivered air. So it's essentially a small percentage of the smaller airflow. So the key takeaway here is that energy recovery systems should operate as intended. As we just learned, the recirculated air from an energy recovery device is exceedingly low when compared to the system amount, and the benefit of the operation is going to exceed the small finite amount of potential recirculated air. So this section I'm going to go over is going to cover how to inspect and evaluate an existing energy recovery system so you can determine if the system is well designed and well maintained. And in context of where we are in the pandemic cycle, a lot of the information on the next few slides shouldn't only be considered during the pandemic, but you should be including these in a post-pandemic environment with kind of in an effort to maximize the benefit of the ventilation during normal occupancy. So the guidance that I'm going to share here, I mentioned before, is based on the TC55 practical guidance operation of energy recovery devices. That document is available on the ASHRAE website, and it's really intended for building operators. First things first, safety. Always make sure that you have, you're using the proper personal protective equipment and that you're adequately ventilating the area and the unit that you're going to be viewing. It's important to keep in mind that the energy recovery component is also a subcomponent of a much larger system, and other components within that system have an effect on the energy recovery's operation, and you're going to need to take that into consideration during the inspection. In general, you're going to look for items that affect pressure, any potential airflow obstructions, or areas of gross leakage or recirculated air. The suggestions that I'm going to demonstrate here are based on the energy recovery technologies that have airstreams that are co-located next to each other. So it's traditionally wheels and plates. So it's important to identify the fan locations and any possible source of reentrainment, as this is going to be used to determine the source of recirculation. And keep in mind that that EATR is an energy recovery device is a function of fan location. So which is ultimately determines your operating pressures. And if you're using a wheel, the carryover or even a plate is you're going to have a small amount of air there. Excuse me, only with a wheel, you're going to have a small amount of air that gets pumped from one airstream to the other as well. So starting with fan location. Fan location is critical as it's going to determine the system's operating pressures. You're going to want to take note, and you're going to take note where they're located. And the inspection is going to require to take static operating pressures. The three most common fan arrangements are displayed in the image to the left. If you find that you have the fourth arrangement, you should really want to contact the equipment manufacturer for advice on how to operate this, as these configurations are prone to excessive amounts of potential recirculation. Each quadrant is going to have its own operating static pressure. And in general, what you're trying to determine is that the pressure scheme naturally wants to move the air from the supply side to the exhaust side. So as a typical rule of thumb, you're going to want to have roughly a ½ inch or greater static in the supply side than you do than the exhaust side. And some of these fan arrangements provide this a little bit easier than others. Okay, so start the inspection of the system. You're going to want to clean the unit with a vacuum to kind of help facilitate the inspection and allow you to see areas where there may be potential for leakage. Um, you're going to want to also clean the heat exchanger surface area as recommended by the unit manufacturer. I'll go over Airxchange's cleaning methods shortly. The two most common methods are using either a vacuum or washing the material with soap and water. And once again, I will include a section on how we perform that on Airxchange wheels. You're going to also, after you're done cleaning, check for gross leakage paths or obstructions that would minimize the airflow being delivered by the system. The easiest way I can recommend in doing this is to bring a flashlight and shine it in different sections of the cabinet. And really what you're looking to do is to see if there's any light penetrating. This could be through fasteners that have been removed, or maybe panels that have been removed over time due to servicing. Really any areas where gross air could recirculate back into the building. Continuing on, you're going to want to check that the bypass or any other damper in the system is operating properly, that they're not jammed, and the damper seals are in good condition. You're going to want to identify the general layout of the system. Look for areas where there can be potential bypass around components. Once again, this could be from missing fasteners or panels. Check for gross leakages. Check to see if the filters are dirty. Dirty filters are going to have a significant impact on operating pressure and subsequently airflow. Lastly, you're also going to want to identify any potential obstructions to airflow. So typically you're looking at filters, coils. In my experience, mist eliminators and bird screens get plugged up pretty badly over time, and these are the devices these are the components that you're going to want to clean and make sure that they're nice and open to maximize airflow delivery. All right, so once the general system has been inspected, you're going to want to inspect the actual energy recovery component itself to see if it's operating properly. Starting with an energy recovery wheel, it's a two-part inspection, one where the unit is on and one where the unit is off. Starting with the units off, what you're going to look for is the wheel clean. It's usually pretty apparent. Here are a couple examples of some dirty wheels. So you'll see dirt or debris on the media. You can see visual gapping or bridging that may be occurring on the heat exchanger. You also want to look for any potential damage. You look for pieces of section that are missing or any structural components that have corroded or maybe be compromised over time. Typical damage, would be significant, corrosion or pitting. So kind of give an example of that. You can take a look at the pictures. These are the things that, it's usually pretty apparent, but can be overlooked if you're not at the unit looking at it properly. You're going to want to check to see if the seals are set properly. Once again, you can use that flashlight method, and you're going to want to follow the manufacturer's suggested method for setting seals. The two most common seals on the market are contact and non-contact seals. Take note of which one you have and make sure it's set appropriately. And lastly, you're going to want to check to see if your device has a purge. A purge is what I'm showing in this picture over here, but it's a mechanical wedge. And it's really there to help minimize leakage in certain situations where there's significant carryover. I like at this point to say that not all systems are equipped with a purge, and really not all systems require a purge. Once again, certain carryovers are acceptable by the ventilation standard. So if you're within the ventilation standard procedure, you sometimes don't need these. But you're going to want to take note if your system does have one of these, and you're going to want to take note of whether it's adjustable or it's a fixed plate, as these settings are going to help determine what the potential recirculation is or what the ATR is going to be when you do the analysis. So for the second part of the inspection, you're going to want to turn the system on. First thing you're going to want to do is determine if the wheel's turning. Now, this may seem trivial, but the first thing you're going to want to do is go to the actual unit itself and not rely on a building management system, because I've seen a lot of false positives in the past. If you have the capability to determine what the RPM of the wheel is, a lot of energy recovery wheels have been equipped with a VFD, and over time, those system settings may not actually be what the equipment manufacturer recommends. So take note of that if you can. Now you're going to want to make sure that the wheel's spinning in the correct direction. I will say that this is usually more critical for units equipped with a purge, because if it's operating in the wrong direction, it can actually siphon air rather than minimize recirculated air. So, once again, some VFDs kind of have a role in this parameter. And, with the system in its normal operating mode and with all the bypass when all the bypass dampers closed, you're going to want to measure the static pressures in each of the 4 compartments that surround the heat exchanger. If the unit has more than one operating mode, you're going to want to repeat this for any subsequent modes. So to assist with recording all this information, within the TC55 document, there's a sample chart that you can use for your specific system. The most critical parts in determining leakage are highlighted in the red area. And again, what you're looking for is essentially a more positive pressure in the supply side of the system than the exhaust side of the system. Please keep in mind that if you have certain fan arrangements, both sides of the wheel may be under static pressure, but you just want to make sure that the driving pressure gradient is from the supply side to the exhaust side. And also you're going to want to, also, as equally important, you're going to want to take down the outside airflows, because that's going to determine if you're receiving adequate amounts of outside air delivery. They want to make sure that you're maintaining those minimum ventilation rates. So now moving over to static plates. So once again, another 2-part process. It's very similar to a wheel. With the system off, you're gonna want to make sure that the unit's clean. Once again, follow the manufacturer's instructions. So typical, you can either wash or vacuum it. But after you go through the cleaning process, what you're going to want to do is you're going to want to see if there's any potential shrinkage of the media or any broken seals around the framing. Once again, use that flashlight trick to see if there's any gross leakages. And at this point, you're going to want to identify the system layout. And identify that in the chart that's provided. Okay, so turn the system back on. So the second part is turning the system back on. And you're going to want to, once again, you're going to follow a similar model. You're going to take the static pressures in all the 4 quadrants that surround the component. If your system has more than one operating mode, once again, repeat this process for all the operating modes. And just like wheels, within that TC55 document, there's going to be a sample chart used for plate-based products. Once again, the critical points to determine leakage are highlighted in red, and the CFM readings, which are critical to determine the airflow, should be taken at this point in the process. Okay, so really the inspection part of the process is used to evaluate whether any type of remediation on the device is required. The general condition is used to determine whether maintenance or service is going to be required. The static pressures are going to be used to determine whether or not changes need to be made to the fan system or control system for the system to operate properly. Once again, make sure that the driving pressures are from the supply side to the exhaust side. After you inspect the unit, if you find that this isn't the case, you'd want to determine the validity of those readings, or consult with the unit manufacturer to see if those readings are consistent with what they would attribute to the system. All the readings are going to basically be used to confirm that the ventilation rate is adequate, and and whether or not a further inspection is going to be required, or your system is good to go. Okay, so inspection evaluation once again may lead to potential remediation depending upon the condition of the system. Typical remediation methods for energy recovery systems is usually cleaning. And for the most part, I'd like to mention that cleaning the media, I'd like to back up. So I'd also like to mention that cleaning the media isn't just a pandemic related task. I know maintenance is often hard to get on particular units, but it really should be part of the normal maintenance and operation of these devices. Cleaning up the media is going to remove the dust, dirt, residue, and any biological contaminants from the surface area. The 2 most common methods for cleaning energy recovery devices is to wash them or vacuum them. You're going to want to choose the approach that's recommended by the manufacturer. For Airxchange energy recovery wheels, we recommend that you wash the heat exchange media, as we find that gives you the best result. Our media is a segmented design, so you can actually remove the individual energy transfer segments from the wheel frame, so you can wash them outside the unit in a soapy solution. The benefit of that is it allows you to really get a really good deep clean of the device. So you basically introduce the segment, and you permanently, or excuse me, you submerge it in a soapy solution, allows that soapy solution detergent to fully penetrate the heat exchange media and really loosen up any, anything that's really accrued on that surface over time. And the other benefit of washing it that way is you're washing it outside the HVAC cabinet, so you don't run the risk of introducing any potential contaminant into the airstream. So quickly to demonstrate that process, I'm going to run a quick video for you. So all of our wheels from 25 inches up to 156 inches have this ability. Not all building operators are aware of it. So I like to mention it because I think it's a very unique process, and a process that really helps building operators make sure that these devices remain at their peak capacity. So once after the segment's removed, the additional materials that you're going to need are, a large container or a tub. You can use that chart on the left to kind of determine what the relative size based upon the wheel diameter you may need. You're going to use a non-acid-based coil cleaner, or really any common soap or detergent. Dawn works great. You'll need access to a water or hose, a soft brush or a vacuum to remove any excess dirt, and really a flathead screwdriver and an Allen key, depending upon size, to remove the segments. So it's not all that difficult. So once you remove the energy transfer segments, the process of cleaning is pretty straightforward. You're going to want to brush or vacuum the surface area just to get any excess residue off the surface. You're going to mix a solution of coil cleaner or detergent in the bucket. And once again, fully submerge that segment in the water. So this is going to allow you to get that good deep clean. In general, the longer you can let these things soak, usually the better the clean is going to be. This could be anywhere from a couple of seconds to a couple of minutes to a couple of hours, depending upon how dirty they are. Then after they're done soaking, remove them, rinse it off with some, just non-pressurized tap water, and put them back into the unit. I should say shake them off pretty vigorously so you remove any excess water, then put them back into the unit. The cleaning process for the Airxchange plate is a little bit different. We don't recommend that you wash the media, as that may damage the component. You're going to want to gently brush and vacuum the surface area, and taking care not to exert too much excessive pressure on it. Just like the wheels, we recommend that you do this outside the cabinet, as once again, it's kind of a more hygienic approach so that you don't introduce any potential contaminant into the unit. And lastly, aside from cleaning, what are some additional remediation strategies? In epidemic situations, it's generally recommended to increase the outside air ventilation to the maximum allowable amount to achieve as much dilution as possible during this time. So long as you're not losing control of the space conditions that would affect occupant comfort. In certain situations, this may be achievable depending upon the design of your system. It's always good to check with a design engineer or with the original equipment manufacturer to determine if this is possible. And I would like to say that units equipped with Airxchange wheels, increasing ventilation and filtration, may be possible through what we call segment swaps. I'm going to discuss this in a following slide, but once again, kind of be aware of the system effect prior to making that operational change of the system. For ERV systems equipped with demand control ventilation, you want it once again to disable that control. And lastly, for ERV systems equipped with economizer, you should check to make sure that the ERV operation is interlocked with the economizer. It really should be, but you want to make sure that that's the case and that the air is properly bypassing the heat exchanger during economizer periods. All right, guys, so if replacing or upgrading filters in the system, now there's been a lot of talk about this. So if you're going from a lower MERV rating to a higher MERV rating, that's going to affect the pressure drop in the system. And, if you're not making any fan changes and you're just adding pressure drop, that's going to minimize the ventilation delivery being delivered to the space. So if you're evaluating a unit that's HRI 1060 certified, you may use those ratings in addition to the site recorder pressures to determine what the relative leakage is. Most energy recovery devices, as I mentioned before, do have a seal system that's adjustable, so you can maintain it over time. You just need to adjust it or replace it depending upon the manufacturer's recommended instructions. And lastly, for not all systems are equipped with a purge, as I mentioned before, and once again, to be honest, not all systems are required to have one. Adding a purge may be done to an existing system, but once again, it's going to have a change. It's going to change the system dynamics quite substantially. So you're going to want to check with the unit manufacturer or an HVAC engineer before just adding one into a system to really determine if it can be done or if it's even required in this case. All right. So if during the process of inspection and evaluation, and we're almost over here, so I know it's a lot of information to throw at you. So if during the process of inspection and evaluation, you determine that you have an air exchange and recovery component, this design does offer the building operator some unique benefit in the pandemic environment. So, as we mentioned before, ventilation and filtration is part of the core guidance from ASHRAE and the CDC. It's often difficult to make these changes to an existing system. One thing you may consider when approaching this is what we consider a segment swap. So where you can achieve either higher airflow, higher filtration, or maybe even a combination of both. So the air exchange segments are interchangeable based upon diameter. And we offer 3 different varieties of segments. We have a high efficiency segment, we have a medium efficiency segment, and we have a low pressure drop segment. And as you move from the high efficiency segment down to the lower efficiency segment, it allows you to either move more air across the heat exchanger surface or lower the pressure drop to compensate for some higher filtration. So looking at the example on the left and starting with the high efficiency segment, if you were to move to a medium or lower efficiency segment, you gain about 0.36 inches worth of pressure drop, which can be used to either move more air if you're not changing anything to the fan system, or increase filtration, as you can see from the transition from MERV 8 to MERV 13, which is kind of roughly the same decrease that you're getting from the segment swap. If going from the high efficiency segment to a low pressure drop segment, it gives you even more allowance, and keep that, it gives you more allowance. So you might be able to achieve a little bit of both. But it's really important to keep in mind, and as you're making these system changes, there's going to be a little bit of loss of performance. Now, in most cases, that loss of performance is compensated by the system not having to work as hard, because during the pandemic, we don't have as high occupancy as we once did. But I just like to demonstrate that there are options available for existing systems in the pandemic environment if you're looking to achieve either higher airflow higher ventilation airflow delivery to the space, or higher filtration, or a combination of both. Okay, so that was a lot of information, and once again, this is very high level review of the guidance from coming from these sources. I highly recommend that you take a look at some of these documents. They may have been updated since I put this together last week, but like I said, things are starting to settle down a little bit. Some resources that are available for you at Airxchange. We have a guide for cleaning Airxchange wheels and other plate components, as well as energy recovery best practices during the pandemic, which kind of highlights what I've spoken about during this time here. As well as some other technical resources that are available to you, depending upon what your concern or what your need is at that point. So once again, thank you. I appreciate everyone chiming in today. I can't really see the chat box right now, but I am going to move over to in a second. So I'll keep this page open so that you have my contact information in case you need to get in touch with me. But I just really want to say thanks again. I appreciate you spending your time with me, and I'm going to move over to the chat box right now to see if there's anything that I can answer.